This week we're going to start learning how to count, and that may sound kind of silly, like it's a simple idea, but counting is actually very complex. And before we can approach these types of counting problems, we need to understand sets, because sets are going to be the language we use to even understand what we're counting. So mathematically, you can think of a set as a collection of objects. These objects are called elements, and we have special notation to denote whether we have an element of a set or not. And so the way I would read that statement in the fourth bullet, I would just read that as X is an element of A, or X is in the set A. And of course, you can put a line through it just like a not equal to say it isn't. Now, the thing is, when you make a definition for a set, because this is math, right, it needs to be very clear and specific to let you know, okay, yeah, this is an element of the set, or it isn't an element of the set. In other words, your definitions can't be vague. And so some examples, you've seen many, many sets. They can involve numbers, they can involve people, they can involve anything. And that's why they're so useful for counting. So we can, again, think of it as a well-defined set or collection of objects. And later on, it will be whatever we're interested in counting or determining the probability of, etc., etc. So I'll show you two different notations that are really common for dealing with sets, and you should be familiar with both of these. And so the first is the listing notation. It really is what it sounds like. So in my first example, I say, okay, let's consider the set of all states that have names starting with the letter A. So in listing notation, what you do is you use a capital letter to represent your set. I suppose I could call this set A. And then you use curly brackets, and then you list out the elements. So in this case, the elements of this would be Alabama, Alaska, Arizona, and Arkansas. And again, all it is curly brackets and a list of the things in your set. You can see how this may become troublesome if you have an infinite number of things. But for example, if I wanted to list all the whole numbers, I could say something like W equals, and I could say, okay, 1, 2, all positive whole numbers, let's say 3, ... and it would be understanding that I keep going with that pattern. And so you can see the idea, like if I look at example 2, the set of all odd numbers greater than or equal to 1 and less than 10, and this is important, greater than or equal to 1, so 1's in the set, less than 10, 10 is not in the set. So, okay, so if I was to call this set, say, B, odd numbers, so that would be 1, and then 3, and then 5, and then 7, and then 9, and we can see why 10 isn't in the set because we're specifying odd numbers, and this would be our set. So you can see it's a way of taking a description of a set and writing it in a more explicit way. You'll see this quite often. Another notation you'll see a lot is set builder notation. It lends itself a little more easily to things involving numbers. So you can see the first example, example 3, the set of all numbers less than 50. Set notation like this, set builder notation, starts with the curly brackets, but then it lists some kind of X or something like that. And then it has a line, and that line means such that, and then some kind of property. So with example 3, if I was to call this set C, I would say, okay, this is the set of all X such that X is less than 50. Notice that this includes decimals, negative numbers, all kinds of stuff, right? This is a humongous set. I couldn't list this out because there's no way for me to list out all the numbers less than 50. And you may say, sure, you know, I can start listing them 1, 2, 3, 4 up to 50 and not including 50. But you can't, because what about 1.001? What about 1.0001? In other words, you can't list these in order. There's too many of them. And so this notation makes more sense. And then you have something like the set of all even numbers. I'll call that D. So you can even just put a property in words there. So this is X such that X is even. So a very nice notation, very compact. You'll definitely see both of these. You should be comfortable with both of them. So the idea of this first section is to really understand sets. We got our notation down. You should know that there's two sets that come up a lot, and that's the empty set. The symbol there, it looks like a 0 with a line through it. That represents the empty set. It's simply the set with no elements. And then the universal set, that's the set of everything we're considering at the time. So we have sets contained within the universal set and the empty sets contained in all other sets. We'll talk about that in a minute. So when I said contained, right? So what does this mean? You can imagine that one set's inside of another set. I mean, a really easy example would be if I said, okay, let's let B equal 1, 2, 3, 4. And let's let A equal 1, 2. A is inside of B, right? The same things that are in A are also inside of B. So what we say here is A is contained in B. And this right here represents that. It's almost like a less than or equal symbol, but not quite. In a Venn diagram, which are commonly used to represent sets, you would have something like this, which would represent our universal set. And then you'd have A, the small set, is inside of the set B. Now this line here means the sets could equal, because technically a set is contained in itself. And so if you really want to specify, hey, this is strictly containment, a proper subset is what we would say, you can leave the line off. Both of these statements would be true here. If we wanted to, again, make it clear that this is a proper subset, we would use this notation down here. So as I mentioned before with the null and the universal set, the null set, the empty set, is considered to be contained in every set. You know, it's kind of a strange thing to say, the set of nothing is contained in everything, but that's just how it is. And then we can also say that every set is contained in itself, which kind of makes sense if you think about it. Containment means if X is in the smaller set, then it's also in the bigger set. So just to run through and make sure we understand these definitions, I have a couple of examples here and we can decide if these statements are true or false. So the first statement says A is contained in B. So that means everything in A is also in B. I look here at A and B and that's definitely not true, so this is false. There's lots of things in A that are not in B. Now, is it true that B is contained in A? So is everything in B also in A? Yes, that's true. So I could say B is contained in A. Now let's take a look at C. It says C is contained in A. So it means everything in C is also in A, but that's not true because you have a 1 here and a 5 here, and those aren't in A. So this is false. The last one says A is not contained in C. Well, that's correct, because if A was contained in C, then everything in A would also be in C, but that's not true. So the fact that it's not contained is correct. It's true. So A is not contained in C is a true statement. This, again, is just running through the definition. This should be second nature by the time we get to counting. So one last general type of set you should understand. So in set idea. So far we've had the null or the empty set. We've had the universal set. We've had the idea of what a set is. And then we also just saw set containment, what it means for a set to be inside of another. One other idea you should be comfortable with is the idea of the complement of a set. So as you can see down here, I have the set builder notation for what this means. So what that's telling me is A complement, that's how you read that, A complement is a set of all X in the universal set such that, remember the line means such that, X is not in A. So if I was to draw a Venn diagram again, so the big set, everything's inside the universal set. And then we have a set A. Everything not in A but inside of U is A complement. So all this stuff out here, everything out here is A complement. Everything left over, essentially. You can say what is left over in the universal set that's not in A. And I think this example down here will help out. So U is 1 through 10 whole numbers. And A is 4, 5, 6, 7, 8, 9, 10. So 4 through 10 whole numbers. A complement is what's ever left over. So if you look here, the difference between these two sets, what's left in one and not the other, would be 1, 2, 3, right? 1, 2, 3 is in the universal set, but it's not in A. So that means it must be an A complement. A complement is everything in U that's not in A. And so together, one way to think about this is together, A and A complement make up the entire universal set. So those are the basic ideas of sets, just how they fit together, how to talk about them. But we're going to also see some operations on sets, and then we'll be able to do counting.